Welcome, and thank you for joining us. My name is Dean Lee, and I'm Professor of Physics at the Facility for Rare Isotope Beams, or FRIB. Today's public talk is part of an initiative at FRIB called the Advanced Studies Gateway. The goal of the Advanced Studies Gateway is to inspire people. We bring together researchers, innovators, creative thinkers, artists, and performers from all fields and strengthen ties between Michigan State University and the community. Today, we have the great pleasure of presenting a public lecture by Professor Chetan Nayak entitled Utility Scale Quantum Computers. Professor Nayak is an American physicist and distinguished professor specializing in condensed matter physics and quantum computing. He is a fellow of the American Physical Society. He is currently a technical fellow at Microsoft and a professor of physics at the University of California, Santa Barbara. His research focuses on topological phases of matter, high-temperature superconductivity, the quantum Hall effect, and periodically driven quantum systems. Professor Nayak leads quantum hardware development at Microsoft. If you have any questions during this talk, please type them into the chat or the question and answer dialog box. At this time, it is my pleasure to introduce Chetan Nayak.
Thank you very much, Dean. Thanks for the very kind introduction and for the invitation to speak here today. So I'm really excited to tell you about utility scale quantum computers. I want to explain what that means, and I'll tell you a little bit about the work that we've been doing at Microsoft, wherein I'll be representing the work of a large team there at Microsoft, whose names I won't try to list right now, but who are on all the relevant papers. So let me start out with a little bit of motivation about quantum computing, okay? So when we think about a quantum computer, and often the way we visualize a quantum computer is we see some image like this, that looks like some kind of exotic thing, maybe sitting in a data center or in an office or a lab. You think about what it really means, at its heart, what it means for something to be a quantum computer, and truly the technology underlying it and the physical manifestation may vary a lot because there are actually different ways that people are trying to build quantum computers based on ion traps and supernetting qubits, topological qubits, spins in semiconductors, and so on. But at their heart, they always have a few things. First they're based on qubits. So classical bits, we're accustomed to doing computation with classical bits, which are just zeros and ones, okay? So instead of using the decimal system, which we grow up learning, where the digits are 0 through 9, computers operate on bits, which are 0 or 1, base 2 system. Quantum computers work on qubits, and qubits actually don't have to be necessarily a 0 or a 1, but can be a quantum superposition of a 0 or 1. Okay, so that's a first important departure from classical bits to qubits. And that enables qubits to have additional computational power over classical bits. A second important feature, and that's called superposition, a second important feature is that correlations can be present in the states of those qubits. So here I have a situation in which we have two qubits, and the values of the two qubits are perfectly correlated. If one of them is 0, the other must be 0, and if one of them is 1, the other must be 1. This is called entanglement. Einstein actually didn't like this at all and called it spooky action at a distance, but it's nevertheless an important part of quantum mechanics and is a critical resource for quantum computing. And then thirdly is interference. We're in the context of waves, we've become used to the fact that waves can interfere. So waves on the surface of a pond, or light waves or sound waves going through two slits, the intensity of the signal that we see over here isn't just the sum of the intensities from the two individual holes in a screen. Rather, sometimes they interfere constructively when the peak of one wave lines up with the peak of the other wave and they add. And in other places, they add destructively when the peak of one wave is lined up with the trough in the other wave, and they actually cancel out. And so instead of seeing just the sum of these two, sometimes it's the sum, sometimes it's the difference, and sometimes it's something in between. And so we see an interference pattern here. This is a common feature of waves, But what's new in quantum mechanics is because of particle wave duality, this kind of interference can occur more generally. And these three things, superposition, entanglement, and interference, make quantum computers rather different from classical computers, and as it turns out, gives them some computational power that we would not ordinarily have. To get a sense of what that could mean, we can imagine emulating a quantum computer with a classical computer. So we're used to using one type of computer to emulate another. You could, emulate a Windows PC on a Mac PC, for instance. But if you imagine emulating a quantum computer with a classical computer, then we have 20 qubits. To do that, you'd need 16 megabytes. Okay, that's not that much. You could do it on a phone, on a mobile phone. But as you continue, the increase is exponential. So with 30 qubits, that's actually 16 gigabytes of classical memory just to store all of the bit strings that you would need to specify states of 30 qubits. And the classical machine now would be a laptop. And if you then went to 50 qubits, well, it's now 16 petabytes. And that's a data center, okay? That's what the classical machine looks like. And if you went to 250 qubits, well, that's more basis states than there are atoms in the visible universe. So the computational power, at least for some problems, of qubits is vastly larger than for classical bits, so much so that even emulating on classical computer, the ability to store the states, just the states of the qubits, just the memory needed, gets out of hand very quickly because of this exponential increase. Okay. Now, having said that, it's important to counterbalance that by saying quantum computers are not going to be better than classical computers, at least initially, at every single kind of problem. Because of what I mentioned about this exponential advantage, you can see that for certain types of problems, as I increase the complexity of the problem or the problem size, the length of time you need in a classical computer is going to take off like an exponential, this blue curve over here, whereas the quantum computer will just be linear, okay? So at some point, these two will cross over. However, the coefficients here, the coefficient of the exponential, the coefficient sitting inside the exponent, the slope of this linear line actually matter. For asymptotics, yes, linear is always going to be better than exponential, but we're not always interested in the asymptotics. We're interested in a specific problem that we want to solve. And for that specific problem, you might be sitting over here if its instance is small enough and the linear is actually worse than the exponential. So what we want is we want those problems for which that crossover time is less than a few weeks, okay? Because we don't really want to do computations where the answer takes longer than a few weeks to get, okay? So as a result, we got to think a little bit about what those prefactors are. And there's a couple things working in favor of the classical computer. If we look at, for instance, a classical GPU like the NVIDIA H200 GPU, well, you can get a lot of information in and out. There's not really the I/O situation is it's 38K gigabits per second, how fast you get information in and out. The processing speed measured in terms of floating point operations per second is 2 petaflops. Quantum processing units intrinsically are going to be slower and have greater bottlenecks. So, with 10,000 logical qubits, with a 10 microsecond logical cycle time, okay, so that's 100 kilohertz. Well, the I/O is a gigabit per second. We're going to be able to do 10 kiloflops. So you can see the quantum computers are intrinsically going to have fewer operations and each operation is slower. Now, of course, with each of those operations, there's this enormous additional power for certain problems. That's this linear versus exponential. But we have to recognize that the slope of this linear and the prefactor of this exponential really give classical computing an advantage for lots of problems, at least for small instances. And so there is work to be done here to find those problems. It's not an immediate slam dunk. You have to find those problems in which that crossover time is less than a few weeks. where these inherent disadvantages of the quantum processor are overcome by its one big advantage of this linear versus exponential here. Okay. So, oftentimes we hear that quantum computers are going to solve all these kinds of problems here, predict the weather, artificial intelligence, the stock market, protein folding, cure cancer, new materials, etc. Most of these don't fit into that paradigm of small data and big compute. Because of the I/O bottleneck that I mentioned, and because we'll have fewer qubits initially than we have classical bits, when we try to even formulate a classical problem, if it involves streaming lots and lots of big data, that's not going to be where the strengths of a quantum computer lie, at least for early quantum computers. So where quantum computers, the highest impact applications are in fact going to come from scientific simulations, which are necessary for things like clean water, designing drugs, new materials, areas in which we have to do quantum chemistry and quantum material science, where we have to simulate quantum systems, are a very natural application of quantum computers. Because after all, what makes those problems difficult is precisely that in order to solve those problems, you have to simulate quantum mechanics. Okay. Unless you think that that's a niche thing, keep in mind that 96% of all manufactured goods rely on chemicals and material science. Everything from consumer and electronic goods, food, agriculture, packaging, water and energy, they all rely on chemical and material science. Okay, and those things impact 100% of humans. Just to give two examples that I like, well, to grow food, to make fertilizers, that relies on nitrogen fixation. Okay, that's actually an extremely expensive, energy-intensive, inefficient process called the Bosch-Haber process. It's over 100 years old. There have been incremental improvements to it, but it's basically the same process we've been using for over 100 years. And it was discovered through trial and error. All the improvements and efforts to do as well or better are based on trial and error. Mostly because we don't really have the ability to really simulate, to predictively simulate these chemical reactions that involve catalysts associated with nitrogen fixation. They're fairly large molecules. They involve transition metals. So they're very hard to simulate. We can't really simulate them on a classical computer. So we have to do experimental trial and error with large libraries of molecules and huge reactors that can do many reactions. On the other hand, with a quantum computer, this is the kind of thing that we could simulate with high throughput, test out and simulation first, many potential catalysts and their reaction pathways, narrow it down to a small set, which you would then actually synthesize and test to see if they're practical. Okay. Similarly, and we know that there are likely to be better, well, I wouldn't say no, but it's likely that there are, in fact, better solutions than what we're using, because after all, bacteria have a much more, at least energy efficient way of nitrogen fixation, which is how plants get it into their roots in the first place. So the evolution has found ways, they don't scale in an industrial way, but that are more energy efficient. What we'd like to do is through simulation find something that's better than what we're currently using. Similarly, carbon capture. We want to reverse global warming. We also would need a catalyst in which we could use to convert CO2 to methanol to take the carbon out of the air. So, and designing catalysts to solve these kinds of problems, which are molecules with hundreds of orbitals, that's going to require at least 1 million qubits. Okay. So that's really, when I say utility scale, the title of the talk was utility scale quantum computers, that's what this means, is that the kind of scale at which you could solve these kinds of problems, and that will require at least 1 million qubits. Okay. Now, why? Where does that million number come from? Because what I said was, this is hundreds of orbitals. Why 1 million qubits? Well, because there's a basic problem of quantum error correction. Qubits are easily disturbed, number one. And because they're easily disturbed, you must diagnose and correct those errors. Now, just to give you a sense of how this could be done, a very simple thing you can do, which is used in classical error correction well, is something like the repetition code. in which I would encode a single qubit, which could be 0, 1, in 3 qubits, either 0, 0, 0, 1, 1, 1. And then if one of these flips, then which you could diagnose, for instance, with a projection operator like this, act with this projection operator to check if the first one is different from the second and third without actually measuring what the information is, because that's important in quantum mechanics. You may have some superposition. You may have a superposition of these two. You want to diagnose the error without measuring or collapsing the wave function or measuring the information you have. That can be done by just checking if the first one is the same as the other two, and similarly with the second and third. And this repetition code allows you to capture a single, if there's a single error, then it lets you find that error and also tells you how to fix it. Because if you find an error, you just flip that first qubit. Again, without measuring what that qubit is. So without measuring what the information is. So there are ways of correcting errors in which a bit flips. Of course, in quantum mechanics, because if you recall superposition, we have to also correct for errors in the phase, the relative phase between different terms in a superposition. That can be done in this, for this simple case of catching one error with what's, not the repetition code, but a simple code, a short code. This involves 9 qubits, so it's forming a state with these 3 qubits, an entangled state with these 3 qubits, and then taking 3 such entangled states and then entangling them. These are what are called now the logical 0 and logical 1 qubits. You can, with this kind of code, catch a flip of one of the qubits. You can also catch a relative phase error between 2 states of qubit. So this is an example of a situation in which you can diagnose all types of errors, of what we call a bit flip error, what's called a sigma X error, phase flip error, or Z error, and also a combination of both, which is a Y error. Okay. More generally, if we want to correct more than a single error, because after all, the longer the computation is, the more likely that you can have 2 errors or 3 errors and so on, then the general condition is we need to take our system with many qubits, find a code subspace within that, so a restricted set of qubits where we'll encode our information, so that when errors occur, errors always take you out of that code subspace in a specific way that you can diagnose the error, that it's left that code subspace, and then you can fix it by going back into the code subspace in a unique way so that you don't end up going to some other point in your code subspace. Okay. And mathematically, this is a condition on these projection operators that if an error of one type occurs and then error of a second type, you always get back to where you started when you project into the code subspace. Okay. Now, what this translates into in general, in terms of numbers of qubits, is if you want to correct many errors, or if you want to be able to run a long computation, we need to be able to run computations in which we have millions of qubits, and they run for millions of steps. And every single one of them could, in principle, have an error in any of those steps, although with a low error rate, with a low underlying error rate. That's the name of the game here, is that those qubits need to be relatively stable. Otherwise, this won't even work. But then, even in the very good situation, for the lengths of computations we want, our logical qubits are going to require 100 to 1,000 physical qubits. So when you then think of 1,000 physical qubits per logical qubit, and you have maybe 1,000 logical qubits, that's where you get into millions of physical qubits. Okay. And if I look at different applications, solving models, for instance, of scientific interest, like maybe solving the Hubbard model of correlated electrons, then to 40,000 plus qubits, you can start to do that. Chemistry simulations with a million, material science simulations, a little bit more. Cryptanalysis, like breaking RSA based on Shor's algorithm, is in sort of in between these two. So these are the kinds of scales we need if we want to have a quantum computer that we can really do something impactful with. And that means, and this is assuming that the ratio between the number of physical and number of logical qubits is less than 1,000. So this is a few hundred physical qubits per logical qubit. If our physical qubits were worse, we would need a lot more physical qubits per logical qubit, and then this gets even more daunting. So for us to scale and to get to that utility scale, okay, we need qubits that are A, reliable, meaning they have low underlying error rates. We need them to be relatively fast because, again, we want our quantum simulation or our quantum algorithm to run faster than the classical one at timescales of around a week. We don't really only want something that asymptotically in the far asymptotic long time limit is better than classical. We want something that's better than classical already at the timescale of week. So it needs to be relatively fast. I put in numbers like, well, 10 kilohertz clock cycle. Well, by the way, that's a logical clock cycle because as you make many physical qubits into a logical qubit, the logical clock cycle or the logical time step will be slower than the physical one by a similar factor. So we need to have reliability without unduly sacrificing speed. We know that quantum computers, their per operation will be relatively slow compared to classical computers, but we don't want it to be too slow. Otherwise, if it takes a month to solve a problem, great. If it takes a year, not so great. If it takes a decade, forget about it. Okay. And then we also need size. We don't want to have the reliability at the cost of making these qubits very large. Okay. Because if the qubits are very large, as we'll see, they often have to be kept in extreme conditions, very low temperatures, for instance. And if they're too large, then it goes beyond what you can do in a cryogenic environment. Okay. And so then you have to consider a distributed situation where you have qubits distributed across many modules. That brings in a whole host of other difficulties and problems. So we do need qubits that satisfy a number of different criteria here that don't always pull in the same direction. We want them to be reliable without sacrificing speed and size, and oftentimes reliability comes at the cost of speed and size. But not always. And that's the idea of a topological qubit, and I'll explain what this is an image of, is based roughly on the concept that, in fact, these aren't always in tension and we can simultaneously satisfy these constraints. Okay. Now, how do we do that? So let me give an introduction to topological qubits. So we've become accustomed to the concept of phases of matter. For instance, solids, liquids, and gases. They have qualitatively different properties, those three phases, that change discontinuously at the transitions between them. So as the solid melts into the liquid can flow, the solid cannot. The liquid then evaporates and becomes the gas. The conditions, the density changes discontinuously at that transition. So there are different phases of matter really with qualitatively different properties, not just quantitatively different. Another example is an ordinary metal, which, for instance, at room temperature, ordinary metals such as aluminum conduct electricity, but they do so dissipatively because the electrons scatter off, for instance, off impurities in the metal. On the other hand, at low temperatures, some metals, again, including aluminum, become superconducting, which means they actually have dissipationless conduction. What happens is the electrons form Cooper pairs, and this occurs at cryogenic temperature. They form Cooper pairs, which is shown schematically here, and those Cooper pairs form a condensed, highly correlated state with an energy penalty, delta, usually called the energy gap or the superconducting gap. That's the energy penalty for an unpaired electron. So superconductors, their basic property, or one of their basic properties, is that the electrons form pairs. They really want to be in these pairs, and there's an energy penalty for an unpaired electron. And in this paired state, they can conduct electricity without dissipation. Now, it turns out that there's a wrinkle in this, there's an additional feature which can occur under special circumstances, and that's topological superconductivity. So in a quasi-1D wire, and what I mean by a quasi-one-dimensional wire is I have a wire that's much longer than its lateral dimensions, than its thickness and its width. So we'll be talking about wires that are a few microns long, and the thickness is maybe 10 to 100 nanometers, okay, the thickness and width. So it's tens of nanometers in those directions and a few microns long in this direction. At those thicknesses, tens to hundreds of nanometers, the energy scale associated with motion in those confined directions is much larger than the temperature. Okay, much larger than other energy scales, no problem. So there's very little motion in the lateral directions, and all motion is along the wire. Okay, and in that situation, it acts like a one-dimensional system because things can just move along the wire, and there's really no motion in the perpendicular directions. These wires that are a few microns long, that's a tenth. If you think about what that length is, that's a tenth the size of a grain of sand. Okay, so hence the idea of the name nanowires. The nanowires that we'll be discussing are combinations of materials. So it's a semiconductor in contact with a superconductor. What you have here is actually a transmission electron micrograph. So it's an image taken not with light, but with electrons that shows how a nanowire like this that is grown by a process called molecular beam epitaxy, which is grown atom by atom in layers. You can see here, in this case, the semiconductor is called indium arsenide. So it's not silicon. It's indium arsenide. It's a different semiconductor. It has applications, for instance, in infrared detectors, like for night vision goggles. But for us, it has other properties that are really nice that we're exploiting here in these nanowires. And what you can see are individual indium and arsenic atoms here. And then on top, it's put into contact with a superconductor, which in this case is aluminum. And you can see the individual aluminum atoms here. And so you can see what we've done here is made a very pristine, high quality interface between aluminum and indium arsenide. And what that combination allows, when it's clean as it is here, and when the atoms are in registry, it lets you have the best of both worlds. It lets you have the magic of superconductivity in pairing, and the great properties of semiconductors, which they're highly tunable. By applying gate voltages, you can change their density. And so by making it clean, you get the best of both worlds rather than the worst of both worlds. And that enables us to, just as if you think about the ice cube versus the liquid, if we take this nanowire in this combination, we apply a magnetic field and a voltage to tune the density, and we're sitting at low temperatures, then as a function of this magnetic field strength, we actually go through a transition. Just like liquid freezes to ice or vice versa, there's a transition here from an ordinary superconducting phase to what's called a topological superconducting phase. Okay? And that topological superconducting phase that we have at higher values of the magnetic field when the voltage is just right, in fact, in many ways, that's like the ice cube to the liquid of the ordinary superconductor. And the way in which it is it has an underlying rigidity, just like ice has an underlying rigidity that water doesn't. This phase has an underlying rigidity with respect to quantum information. So it's a more abstract version of rigidity. What the topological phase has, the property it has, is unlike the ordinary superconductor where there's really this big penalty for having an unpaired electron, the topological superconductor actually is okay with an odd number of electrons. When there's an odd number of electrons, that odd electron can actually be accommodated, okay? And the way it accommodates is it is in the bulk of the super. There's no place in the superconductor where you can find that odd electron. Everywhere you look, the electrons are paired up and in this correlated state. What happens when you have an odd electron is there are, at the ends of the wire, what are called Majorana zero modes. And that additional electron, instead of being anywhere in the wire, is accommodated by the Majorana zero modes at both ends. Okay, so it's not any localized place. There's no way to localize it and say, I've got an odd electron here. It's actually, in a sense, shared between the two ends of the wire. And only through the correlations between them could you tell whether it's an even or odd number. So if you were to bring together the two ends of the wire in some way, then you would be able to see, aha, I've got nothing there. It's an even number of electrons total in the wire. And if I bring them together, I might instead see, aha, there is an odd number. There's this extra electron. And this is the difference between, this wire may have 1 billion electrons. What we're talking about here is the difference between 1 billion and 1 billion plus 1, this even or oddness. So the total number is hardly distinguishable at all. And in many cases, it isn't distinguishable. it's only the even or oddness or parity that distinguishes the two states. And it's not, and the reason that it is that the topological superconductor can accommodate this in the ground state is that you never have to have an unpaired electron in the normal sense of an electron that's sort of looking for something to pair with. That additional electron actually is put into the ground state and shared between the two ends. So what we need in order to be able to use this for quantum information is we need some fast, accurate measurements that can distinguish the 0 from 1, that can effectively take the two ends of the wire, bring them together, and check, do I have an even or odd number of electrons? Where again, we're trying to distinguish between 1 billion and 1 billion plus 1 electrons. So that's what we need. And of course, that's provided we have the topological superconducting phase in the first place. Okay, so now let's be a little bit more specific and discuss, okay, how actually do we make this topological superconducting phase? Okay, in these proximatized, what are called proximatized semiconductor nanowires. So we have a semiconductor nanowire, some kind of barrier layer that regulates the coupling between that semiconductor and a superconducting layer. Here I have an equation here that describes a simplified model of the physics of such a system. What this model encodes is, this is the bottom of the conduction band in this semiconductor, and the various terms in this model Hamiltonian account for the fact that we need our semiconductor to have, first of all, large spin orbit coupling. So that's a coupling between the intrinsic magnetic degree of freedom of the electron and its motion. And for us, large means a specific thing. It's 4 millielectron volt nanometers. What that does is when it's large, that if you look closely, the bottom of that conduction band of the semiconductor actually is split into two helicities. We need something called the large G factor, which is how strongly the electrons in the semiconductor react to a magnetic field, how much their intrinsic magnetic moment reacts to a magnetic field. If these electrons were sitting in the vacuum somewhere, that G factor would be approximately 2. Very famously, it's not exactly 2. It's a little bit different from 2. And that has to do with subtle effects in quantum electrodynamics. But inside of a material, inside of a semiconductor, the number can be quite different from 2 because of the motion in that solid. And in fact, in some semiconductors, it can be large, 10 in the range. And for us, we actually, that's very beneficial for us. We want it to be in the range of 10 to 50 even. And if you recall, and I'll say a bit more about this, the reason for that is because we needed to put on this magnetic field. And we like a relatively small magnetic field to have a big effect in the semiconductor without disturbing the superconductor too much. And so, in fact, in semiconductors, the G factor can not only be very different from 2, like in this case, large, it can actually have the opposite sign. So in indium arsenide, that G factor is actually minus 10. And then what we need is we need control over the density. Okay, if we can tune the density just right, and that's, again, that is one of the key properties of semiconductors is that you can tune the density so well, then if we put the chemical potential here, where there are only these 2 Fermi points, where it only intersects this at 2 points, then you'll end up, when you have contact with a superconductor, you'll end up with a topological superconductor. Okay. And what the phase diagram of this looks like is, as I, on this axis, change the magnetic field, this is the Zeeman energy associated with that magnetic field. So it's proportional to the magnetic field and to that G factor. Or change the density by changing the chemical potential here. Then I'll drive a topological phase transition from the kind of ordinary or trivial superconducting phase, depicted here in blue, into the red or topological phase over here that occurs at high magnetic fields. There's no political statements being made in the color scheme here. Just want to be clear, I'm just distinguishing topological from trivial. I guess those of us in California have heard that there's an election going on in Michigan and places like that. So you probably are inundated with that. But here I'm only trying to distinguish trivial and topological phase. Now,
So Chetan, maybe I can ask a question for
Yes.
those who are not that familiar. So how would I know that I'm in the topological phase as opposed to the normal phase?
Yeah, great. So the topological phase has these Majorana zero modes at the ends. And so when the topological phase can accommodate in its ground state either an even or odd number of electrons. That has a variety of signatures. One is, and if you just hang on to that question for 1 second, I'll return in a minute, but let me just give you the short answer, which is, one is you can tunnel electrons in and the system can accommodate them at zero energy. You can just see, if I look at the current versus voltage curve, it'll show some feature at zero energy. That's one important. So over here, you'd expect that. Now, it's more subtle for reasons that I'll explain, because there may be accidental reasons why there might be zero energy states, even in the trivial phase. So you got to be careful about that. The second thing is, if you recall, phase transitions involve these discontinuous changes. So as I go from blue to red here, that boundary is a phase transition point where something changes. It turns out it's a second order phase transition. So I have to look at the right quantities, but there's a diverging length scale and there's a vanishing energy scale because the energy gap actually vanishes at that point. So what you can see is, as you cross this phase boundary, you see an energy gap close and then reopen on the other side of the transition. And where it reopens, you have the ability to inject current at zero voltage, at zero bias voltage. Now, on top of that, of course, you should be able to just check, does the system accommodate even or odd numbers of electrons equally well, just directly, right? Now, another way of saying it is, the topological phase, you can just make a qubit with it, okay? So those are the ways. And over the next couple slides, it'll be a little more clear kind of what I mean by that, okay? And that's a very important question, because what I just discussed was a simplified model that's very highly idealized. Now, the real world is more complicated. And actually, for us, the name of the game is, how do we make the real world as close to that model as possible, okay? Through device design, through fabrication, through improved processes, and so on. So in real devices, superconductivity is more complicated because there's disorder. So even though I showed you this transmission electron micrograph where you saw all the atoms sitting there perfectly, if I look over long enough scales, it's never quite perfect. There are some defects that you just can't pick up in transmission electron micrographs. In addition, as we fabricate devices, those fabrication processes necessarily cause some damage, okay? And many of the additional layers that we have to put on in order to make devices are not quite as clean, and in some cases are much less clean than that perfect superconductor semiconductor interface that I mentioned. In particular, disorder will actually just wipe out and destroy the topological phase. So when I said, hey, we need this thing to be clean in order to get the best of both worlds, that's what I was referring to. Because if it's not clean enough, then what happens is, and that is measured by what's called the localization length, which sort of says how far an electron can go without scattering too much. The localization length needs to be larger than the coherence length. And the coherence length is essentially the size of a Cooper pair. That translates into, in a certain family of devices, into a criterion that everything needs to be uniform, that the surfaces can't have roughness, the various layers can't have variations that are larger than on the order of 1 to 5 nanometers. Is a scale of variations, depending on which particular geometric parameter. All the geometric parameters need to be uniform to roughly that scale. And then the density of defects in the dielectric, at the interface between a dielectric and the semiconductor, needs to be less than around, it's a specific number, it's not a magic number or anything, but it's what comes out of our simulations, around a few times 10 to the 12 per centimeter squared. So a key thing is to check to make sure that the uniformity, that you're able to make devices that satisfy this kind of uniformity. I mean, this is the uniformity of that interface between the semiconductor and the superconductor, but there's many other geometric parameters when we look at complex devices. And we can extract these density defects. Some of these defects we can't see in imaging, but we can extract them by looking, for instance, at mobility as a function of voltage and by fitting it to theory. So making clean devices is extremely important. Without it, the topological phase would be destroyed. Okay. Now, that is something we've accomplished. I would not say we're in the very low disorder regime. We're really more in the intermediate disorder regime. But topological phases can survive the intermediate disorder regime when the localization length is a little bit, but maybe not 10 times larger than the coherence length. And in that intermediate regime, we have devices like here's a scanning electron micrograph image of one of our devices that actually have the topological phase. Okay. But because of the disorder, the phase diagram looks quite a bit more complicated. Instead of this simple parabolic phase boundary like here, the phase diagram ends up looking much more complicated. And this is a zoom in, it ends up looking like this. Now the axes here, this is actually a magnetic field. This is, it looks like I got cut off here, but this is voltage over here. So this is no longer a simplified model. This is, the real device. This is experimental data. So the knobs, we tune our voltage on one of these gates over here and magnetic field. And red is still topological and blue is still ordinary superconducting phase. And what you see is the topological phase has shrunk a lot, okay? It has kind of an irregular shape, which varies a little bit from device to device, depending on where exactly the impurities happen to be. I've introduced an additional color scale here, which shows kind of darker red is in the topological phase, but with larger gap and energy gap. And the darker blue is in the ordinary superconducting phase, but with larger gap over there. And so you can see there's a lot of sort of pale regions over here where the gap is really small. And that's because of disorder, the system is sort of broken up into regions that are topological and regions that are trivial or ordinary superconductor. And there's lots of boundaries in between them that have low energy states. And that's kind of this messy and homogeneous region that you see that has these pale colors with very small energy gap. But there is a topological phase. It's smaller because of the disorder. And this is something we've seen in multiple devices, and we kind of routinely can make things with this intermediate level of cleanliness. In the long run, of course, we want something that's extremely clean. It's in the very low disorder regime, but right now, where we are is this intermediate regime. Okay. Now, so that's the, having the topological phase in the first place. Now, let's come back to this question of how do we do anything with it? And, this is a special case, of this Majorana zero mode or topological superconductor story. It's a special case of what are called of the general concept of topological quantum computation and anyons. And the idea there is we encode quantum information in states of what are called non-abelian anyons. And there's two basic processes you can have with them. Just fusion. You have two particles. They carry some topological quantum numbers. And what you want to know is what is their combined topological quantum number. Now, if this were electrical charge, it would just be addition. You have charge 1 and charge 1. The combined charge is always charge 2. But if this were spins, for instance, the addition is more complicated. You can have a spin a half and a spin a half, and their total spin could actually be spin 0 or spin 1, because the two spin a halves can form a singlet and have spin 0, or they can form a triplet and form spin 1. Topological quantum numbers are closer to that. They're not exactly like that, but they're closer to that, where they have what are called fusion rules, so that the rules for how you combine topological charges is complicated. And so what you measure when you measure the combined topological charge of two of these anyons, the output is basically the primitive measurement that you do in order to read out the answer in a computation, for instance, or in quantum error correction to measure and find errors. And the basic gate or the basic processing operation is braiding. You take two of these anyons and you exchange them. And the reason that this is, that this is an attractive concept is that if I look at braiding or fusion for that matter, let's focus on braiding for a moment, then the specific path in which I braid them doesn't matter. It's still an exchange. It's still a counterclockwise exchange of these two particles. So another way of saying that is it's very highly resilient against errors, because errors in the specific path in which I braid them don't matter. Okay, up to small corrections. So the topological qubits, they have very low gate infidelities, which are controlled by that energy scale delta. Of course, if that scale isn't very large, then you may end up exciting thermally or through motion. You may end up exciting additional anyons, and they may come in and unintentionally braid these and cause errors. So you do need this energy scale delta to be large, but in that limit, you can see how this is an extremely robust process. So we wanted qubits that are reliable. Okay, we have a large topological energy gap. We're great. But it turns out the gate times and the size are inversely proportional to that. So actually, if that energy scale is large, we actually can satisfy all of our constraints. We can have something that's reliable, we can have something that's small, we can have something that's fast. So that tension between those three things is actually reduced. And our goal when we say how reliable should it be, how small should it be, how fast should it be, we want something that has a per cycle, per qubit error rate that's less than 10 to the minus 4. That's the point at which quantum error correction becomes very, very efficient, okay? That you're not just sort of at that break-even point where you're basically running in place and just barely managing not to create more errors than you can correct. That's the point at which you really have sort of exponential scaling towards something that's extremely precise or extremely low error rates. We want our length scales to be less than around 10 microns. That way we could have 1 million qubits on a centimeter by centimeter chip. And we want our operation time, our fundamental operation time, to be around a microsecond or faster, because that enables us to do, let's say, a chemistry simulation involving 1 million physical qubits and 1 trillion operations. You could solve that in a month, okay, if you have a 1 microsecond operation time.
So,
Yes.
Chetan, there's a question from Anjali Agrawal asking, is the A and B label shown here after braiding a mistake? I guess it's
sorry, it is. Yes, that's a typo. Sorry, these are B and A. Thank you. Thanks for pointing out. Absolutely. Okay, so those are really the targets we have here, are that level of gate infidelity, size, and time scale. Okay. So now let's talk specifics with indium arsenide, with aluminum, a hybrid device built on that, and how do we actually read out that even or oddness, that fermion or electron number parity. Okay. So the way we do it, this is kind of a minimal version. I'll show you what a more complex version with more bells and whistles would look like. But here's kind of a minimal version. We have 4 of these Majorana zero modes here. Okay. The way we do that is we have some topological regions and some trivial regions or ordinary superconducting regions. The Majorana zero modes live at the boundaries between those. And we, in addition, have quantum dots. And you think of a quantum dot as just a small confined region where electrons can sit inside. It's like a small corral. And they're small enough that the spacing between energy levels is such that it is large compared to the temperature and all of the other scales in the problem. And when this quantum dot is coupled to the wire, where we have these Majorana zero modes, the energies are sensitive to that parity, that even or oddness. And the reason is because an electron can tunnel from the dot to the wire and back, and that changes there's some energy associated with that. It can tunnel from the dot to the other end of the wire and back, or it can tunnel to the wire and come back from the other end and go through a circuit. In so doing, and going through the circuit, because it's an electron, electrons are fermions, it has to get past all the fermions in the wire, which is, it has to do a number of exchanges, and you pick up a -1 every time 2 fermions get exchanged. And so as a result, it keeps track of whether there's an even or odd number of fermions in the wire. That process is also sensitive to the magnetic flux through this loop via the Aronoff-Bohm effect, and so it's sensitive both to parity and magnetic flux. And by varying magnetic flux and parity, we can see that dependence. The energies as a result of this dot wire system actually look like this. There's an avoided crossing in the energy spectrum, and the size of that avoided crossing depends on whether Z, the fermion parity, is even or odd. In one case, you have a very small avoided crossing, in the other case, a larger avoided crossing in the energy spectrum. And that avoided crossing in the energies translates, the capacitance is the second derivative of energy with respect to voltage, translates into, this is an analytic expression in certain limits, simplified limits, but it translates, the capacitance is essentially the curvature of these curves. And so you can see, depending on whether Z is plus or minus 1, so even or odd parity, you will either see a capacitance that's large because there's a big curvature here, or smaller because there's these red values here with less curvature. And that's the thing that we want to be able to measure. Okay. So that's very schematic. Here is, putting in some more of the important physical details. What I'm now showing is the various gate layers that are necessary in order to define both the wire and the quantum dots. Looking at this from an angle, here's what it looks like. It's building on our earlier work where we first showed we have the topological phase. It's got what's called a gate-defined nanowire. So these various gates that are over here define a nanowire that's based on an indium arsenide quantum well. So it's indium arsenide. By quantum well, we mean that the electrons are confined to live in flatland and only move in this two-dimensional layer of indium arsenide. With the gate, there's an aluminum strip here. So there's a roughly 60 nanometer wide and several microns long aluminum strip. And that aluminum strip, underneath that aluminum strip is the active region where we induce superconductivity in the semiconductor. We've got these gate layers, two gate layers. And what they do is they deplete the electrons everywhere else except for under the strip. That enables you through those electric fields, you've defined a wire, a channel right underneath the aluminum that is your nanowire. And it also defines the peripheries of the quantum dots and varies the densities in the quantum dots, the charge in the quantum dots. Looking at it from the side now, you can see here's the aluminum strip. Here's the dielectric, which is one of our big sources of disorder, various gate layers. Here's the indium arsenide quantum well, and the active region of the wire is sitting right here. Now, this device has been heavily optimized through simulations so that the junctions, the size of these quantum dots, the charging energies, and so on have been optimized so that when we measure the capacitance, so it's the capacitance of this dot you have here, of the gate to the dot, that capacitance has a flux dependence, okay? The flux through this loop that looks like this. Depending on whether the parity in these Majorana zero modes, and therefore in this wire, is even or odd, you either see this pink curve here or the blue, okay? They both are individually H over E periodic, so periodicity of a flux quantum or two magnetic flux quanta, and offset from each other by phase pi. And very importantly, you want to know, can I distinguish these? Even in the optimal case where I sit right here, where they're as far apart as possible, can I distinguish them? And the answer is, this has been optimized so that that capacitance difference is a femtofarad, which is actually a relatively large capacitance that is measurable. Now, an important subtlety so that's great. In a device like this, we can get a measurable effect. It can be big, but there's an important subtlety, which is that something called quasi-particle poisoning can happen, which is, as I said, in the ground state, the nice thing about topological supernovas is that even in the ground state, they can accommodate even or odd number of electrons. But the system may not quite be in the ground state. An external particle could flip the qubit state, so you could have infrared radiation come in, break one of those Cooper pairs because it supplies that energy. You then have an unpaired electron that goes and gets absorbed by your wire at the Majorana zero mode, and it now flips the state of the qubit. So we need our fermion parity. When I said we need it to be very accurate and fast, of course it has to be fast because we want to operate our quantum computer fast, but it also has to be faster than this poisoning time. This tau QPP is a quasi-particle poisoning time. And if it's faster than that time, then if we just monitor our device, then what we'll see is with each measurement, we'll see either on the red or the blue or the red, and we will see some occasional jumps in between them, that jumping back and forth as we go over time scales longer than this quasi-particle poisoning time. Okay. So we need our measurement time to be shorter, and then we can monitor over longer times. Okay, take a time trace. The way we can do a measurement like that is through what's called dispersive gate sensing. So we put this gate, embed it in a readout circuit that's basically an RLC circuit, and the RF, the radio frequency response, and in our case, this is at around 600 megahertz, the radio frequency response of this circuit can be measured. It varies as the capacitance changes. So remember, the capacitance changes, and the shift depends on the state of the qubit, which is the fermion parity. The resonant frequency of this circuit is, it's basically an LC circuit as far as resonance. So as you change the capacitance, you change the resonant frequency. that change in resonant frequency actually means that even the off-resonance RF response, if I send an RF wave down, it's going to come back phase shifted. The amount of that phase shift depends on that capacitance. So that's the thing we measure, and that's something we can measure actually quite rapidly. Okay. So now in the remaining few minutes, let me show you some data from such a measurement. So here is our topological qubit device. These are false colors distinguishing the first and second gate layer. I'm going to focus on this left part of the device. And here's what we observe when we measure that capacitance. We tune the nanowiring to the topological phase. We sit there and we monitor the capacitance shift, or the real part of the capacitance shift, as a function of time. And what we see is, in fact, a random telegraph signal. Okay. The difference between the two values that we see is around a femtofarad. So we interpret this as one of these is the 0 state of the qubit, one of them is the 1 state. The time scale for these switches, or rather the time scale for the dwell times in the up and down state, exhibit a Poisson distribution. So they fall, the histogram of dwell times falls on exponential decay as a function of dwell time, with a time constant of about 2 milliseconds. So that really means that these are not extremely frequent. It's only every 2 milliseconds, roughly, that we have one of these quasi-particle poisoning events. And we can measure much faster timescales. We can measure in a few microseconds. This is what we generically see. When the perpendicular magnetic field that tunes the flux is a multiple of 1.7 millitesla, we don't see any bimodality. We just see kind of the inherent noise in the system. What that means is that not only is there bimodality and random telegraph signal, but it's very strongly flux dependent. To identify that flux dependence, we take a histogram of values, so just bin the values that we see in that bimodal signal. And as a function of perpendicular magnetic field, you can see that it is bimodal. It's roughly h/2e periodic, and that bimodality is flux dependent. So where you saw that big, clear random telegraph signal, that was right here, where there's this big bimodality at kind of the optimal flux value. And where we saw no bimodality, that was right here at the destructive interference point, where you don't expect to see any bimodality. Okay. So if we compare this to simulation, there's the crossing points between of course, in the experiment, nobody tells us what the colors are. But what you see if you compare measurement to simulation is that there are these crossing points, and they're the points where there's the largest difference. And at that largest difference, it's about a femtofarad. Now there's additional complexity in the measurement. You can see that the measured values don't fit exactly what's in the simulation here. And that actually has to do with details of the resonant circuit. So there's an inductor in this resonant circuit, and that inductor also has some magnetic field dependence that makes this look a little non-periodic. So some of the additional experimental complexities give additional structure here, but the basic feature is the same as what we have in the simulation. Again, with the right scale associated with it. So we interpret this as we've observed fermion parity encoded in 2 Majorana zero modes. Those switches are caused by quasi-particle poisoning of Majorana zero modes with that 2 millisecond time scale. We can discuss the accuracy of that measurement. So if I measure some value of the capacitance and I want to say, is it 0 or 1? Well, you might just measure some point here, or you might measure a value here. Here we're using both the real and imaginary parts of the capacitance here on these axes, but you can see the imaginary part doesn't do much. What's key here is there's some Gaussian spread because there is noise, and the size of these two Gaussians is much smaller than the separation between their midpoints. Okay, that means we have a large signal-to-noise ratio, and if we integrate over 90 microseconds, actually the signal-to-noise ratio is 5. Okay, or if I only integrate it for 1 microsecond, that's a signal-to-noise ratio of 0.5. The optimal value is around 30 microseconds, and there's an assignment error for these measurements of about 1%. Outside the topological regime, by contrast, this is what boring looks like. We either see, outside the topological, we either see no bimodality whatsoever, you just see kind of nothing. Then this is sort of just the underlying behavior of the resonator with field. Or sometimes you do see bimodality, but no flux dependence. And that we interpret as there's some kind of low energy accidental state at one end of the wire. You can tunnel from the dot to that end, but there's no circuit, which would give you flux dependence. Okay. That quasi-particle poisoning time of 2 milliseconds is actually consistent with the density of about one unpaired quasi-particle per micron cube. So that's like less than one per device, essentially, on average. But we can actually, to check our interpretation, can increase that by injecting current. Some of that current goes in as quasi-particles, and by injecting more current, we can make the quasi-particle poisoning more rapid. And you can see that that time scale decreases as we inject more current. Okay. We can do a bunch of other checks, disconnect the dot from the wire, the effect goes away, and so on. So there's a lot of additional evidence that this interpretation is correct. So just to wrap up, since we're at the top of the hour now, so just observations and next steps. The thing we really need to be able to do is we want to be able to process the information stored in technology. I think we can check that box. We can get an SNR of a half in 1 microsecond, or an SNR of 5 in 90 microseconds. So we can do rapid, accurate measurement of topological charge. Okay. We of course want to make it more accurate so that we can do this more rapidly. So we want an SNR that's larger than 1 in 1 microsecond, and that involves, reducing the noise through a better operation or better amplifier, better low noise amplifiers, increasing the signal by basically, suppressing the parasitic capacitance relative to which the interesting quantum capacitance is changing the system. We also, as I mentioned, for multi-qubit devices, there's a different design we're going to use that enables more kinds of these kinds of measurements, including 2-qubit measurements. The other thing we need is we need to be able to, as I said, reproducibly create the topological phase in devices. That we have done, but in future we want larger topological gaps greater than 50 micro eV, so that you'll have more stable topological phase with lower error rates. So with that, let me stop here and take more questions.
Thank you very much, Chetan. It's a beautiful talk. There's a question from Chris Gould asking about what's the longest time people have kept qubits around without them degrading through various means like cosmic rays, radioactivity, etc.
Yeah, so it's a good question, and the answer is, it depends on the units you're using, because really you should measure the qubit lifetime relative to the the operation time, right? So if a qubit operates extremely slowly, but it lives for a long time, that's not that helpful, right? So you really need to kind of, to consider it relative to, to the operation time. And secondly, if you have a single isolated qubit, that can often be very long-lived, but you can't do anything to it. If you isolate the qubit extremely well, sure, it might live a long time, but you also can't couple it to another qubit. And so what you really need is you need to consider it in the context of, a multi-qubit system. So, taking those caveats into account, I would say where we are roughly is the lowest error rates are, they're sort of almost 3 nines. So, the error rate per qubit is close to 10 to the minus 3. It's between 10 to the minus 2 and 10 to the minus 3. Mm-hmm. So that's probably, and that's true in various different types of qubits, superconducting qubits, ions, neutral atoms, etc. Mm-hmm. Semiconductor spin qubits, they're all sort of in that level of per qubit, there's 1 error every 1,000, steps, mm-hmm. But it's not quite 1. It's sort of like, it's somewhere between 5 and 1 errors per 1,000 steps, sort of like that. Mm-hmm. Maybe 3, yeah.
Yeah. So if there are any other questions for Chetan, go ahead and put them in the question and answer or the chat. Maybe I'll ask a question. So how much more time do you think it will be to have a topological qubit with gate errors where you make 2-qubit entangling gates at the level of 10 to the minus 4 or so?
Yeah, so I would say Microsoft, we don't talk about our internal timelines publicly. So I can't give you a very concrete answer to that. But I'll say we're making significant progress towards that. So stay tuned. We'll have results in the not too distant future.
Great. There's a question from Anjali Agarwal. Can you comment on the design of multi-qubit devices?
Yeah, so I think so. There's a couple of things. Of course, is one qubit versus multi-qubit. Of course, the multi-qubit device, we want to enable coupling between qubits, and for multi-qubit devices. So that's one thing, we want to enable coupling between qubits. And actually, the multi-qubit devices should be designed, I think, with an understanding of what the quantum error correcting code is that you're going to use. So the layout of the qubits really should reflect a particular quantum error correcting code and the native operations you have. Even within a universal quantum computer, there are some operations that are sort of native operations that you can do out of the box, and there's some that you have additional overhead associated with them because you need to run a long circuit to do this one step, and you need additional ancilla qubits for workspace. So a lot of these sort of order one numbers matter, and so I would say design of multi-qubit devices should be done of course, to make the 2-qubit gate error rates as small, 2-qubit entangling gate error rates as small as possible, but also to facilitate or really co-designed with quantum error correcting code.
Okay, very good. Let's take one last question from Virginia Ayers. What is the purpose of the barrier layer? Is it externally applied or the natural interface that develops? Thank you.
Yeah, that is an excellent question. So I didn't have time to discuss this. Let me go back for a moment to the to the appropriate figure. So here you can see there's indium arsenide, and then there's this barrier, this top barrier, and then the aluminum's over here. The purpose of the barrier layer is twofold. Number one, we want to induce superconductivity from the aluminum into the semiconductor. This is what's called the proximity effect. And what that means is the electrons in the semiconductor can tunnel into the superconductor, can spend some time in the superconductor, and then come back. And when they come back, they sort of bring that pairing back with them, right? So it's like two electrons in the semiconductor hop into the superconductor. In the superconductor, they're paired, and then they can come back and they still sort of remember their pairing. So that's great. So we want to induce superconductivity. So we need a healthy and robust interface so that's relatively transparent, so that you can get electrons to hop into the superconductor and back. We want a lot of tunneling into the superconductor, but we don't want too much, because if the electrons spend too much of their life in the superconductor, then actually in the superconductor their G factor is not 10, or actually it's not -10, it's +2, because in aluminum the G factor is basically the same as in free space. So the G factor instead will be renormalized downward from its really good large value of indium arsenide. The spin-orbit coupling, which is larger than 4 MeV nanometer, if it spends too much time in the aluminum, that will also be renormalized down. So we want to inherit the good properties of the superconductor without losing all the great properties of the semiconductor. So the barrier needs to kind of allow the optimal amount of superconductivity to be induced, which is roughly the induced gap in the semiconductor needs to be roughly half the parent gap in the superconductor. So the barrier layer, it's extremely important to engineer it so that you get the right amount of superconductivity in the semiconductor. There is actually a Goldilocks regime there where it's not too much and not too little. Now, the barrier layer actually has to do a second thing, which is one of the main sources of disorder. All this relatively pristine semiconductor growth, and actually even superconductor growth, all done within the MBE machine, ultra high vacuum, high purity. The dielectric is one of the places that's dirtier. It's an amorphous material like aluminum oxide or hafnium oxide. And so there is significantly more disorder, particularly at the interface, but not only at the interface, within the dielectric. So we want the barrier layer, if possible, to keep that disorder as far away as we can. So a thicker barrier is actually helpful for keeping the disorder further away. If this quantum well were buried far beneath the surface, then it would be much cleaner because it'd be very far away from disorder. However, of course, you can't put it very far down because then you wouldn't get any superconductivity in. So again, there's kind of a Goldilocks regime where you're getting the right amount of superconductivity, but not too much, and you're getting as far away as you can from the impurities, or at least one of the main source of impurities, but not so much that you crush the superconductivity.
Mhm. All right. Well, thank you so much, Chetan. That was really, really great. Let me stop the recording.